Hello students, in this video we are going to focus on common drain amplifier. So in common drain amplifier, the input source is basically connected to the gate terminal and the output is basically taken out from the source terminal so that the drain is common to both the input and the output. And basically there are two types of loads that can be attached to the source terminal. One being a resistive load and the other one being the current source load. So now we will focus on common drain amplifier with a resistive load. So as I stated, the Vout is taken from the source terminal whereas the Vin is connected to the gate terminal of this transistor M1. Now we will try to plot the voltage transfer characteristic graph by directly inspecting the circuit. So the VTC or the voltage transfer characteristic graph is nothing but it's a plot between the Vout and Vin. Now, what happens when our Vn is less than the value of Vt? The current or the transistor M1 basically will be in cutoff, and because of that the ID will be equal to 0 and the Vout, which is basically defined as the current times the resistance RL, and since the value of ID is equal to 0, the Vout would be equal to 0 in that case. But what happens when the value of Vn starts increasing more than the value of Vt? So let us assume that the value of Vn is slightly just greater than the value of Vt. In that case, the value of VGS is very small, and due to which there will be a small amount of current that flows across RL resistance. And as we know, the Vout is nothing but it's a product of current into the resistance, and since the value of current is pretty small, the Vout will also be very small. And what happens once the value of Vn keeps on increasing more than the value of Vt? In that case, even the value of Vout will start shooting up, which means that the source is following the gate terminal as we increase the value of Vn beyond the value of Vt. So based on this particular description, we can right now try to plot the voltage transfer characteristic graph of this common drain amplifier. So as stated in the first case, where when the value of Vn is less than the value of Vt, the output is basically 0. Now once the Vn crosses the value of Vt, there will be a graph which has a linear relation between the value of Vn and Vout, which means that the higher the value of Vn that we increase, the Vout also rises by the same amount. And that's the reason why the common drain is also called as a source follower, which means that the source node is following whatever changes that is happening across the input. And now let us try to evaluate the small signal gain for the circuit. Now the evaluation of small signal gain can be performed by two means. One being using a large signal analysis, and the other one using a small signal analysis. Since we have done the gain calculation for the circuits that we have discussed earlier through the small signal analysis, this time we are trying to find the gain through the large signal analysis method. Now let us move on to the large signal analysis, for which I again draw the circuit of common drain amplifier with a resistive load RL, and Vout is taken from the source terminal and Vin is fed to the gate input of transistor M1, and the drain is basically common to both the input and output, and that's the reason why it is called as a common drain. Now the composite signal Vout could be written as a product of composite current ID that is flowing across the resistance RL. And the gain of the circuit can be computed by performing a partial derivative on Vout with respect to Vn across the Q point. As we have discussed, this is the Q point over which we are going to perform a partial derivative on the Vout expression. So when we perform this partial derivation, what happens is the current basically changes. So the partial derivative towards the right hand side will be returned as just del ID divided by del Vn. Now let us try to expand the current expression before we perform the partial derivation. Now this ID is nothing but half Kn dash W by L VGS minus Vt the whole square into 1 plus lambda VDS. Now here we have included this second term, that is 1 plus lambda VDS, to actually model the small signal parameter R0. And before we perform a partial derivation upon this current ID, we just need to expand the values of VGS, VDS and VT. Now let us try to expand the value of VGS. So VGS could be written as VG minus Vs. Now what is connected to the gate terminal is nothing but the input signal Vn. So which is nothing but Vn. And what is connected to the source terminal is nothing but the Vout, which could be written something like this. And similarly, the VDS could be written as Vd minus Vs. And again, what is connected across the drain is nothing but the DC potential VDD, and what is connected across the source is nothing but it's the same Vout term. Now, because the source terminal is not at the same potential as the body of our NMOS, there will be a body effect problem, and because of that, the threshold voltage is no more equal to VT0. It has to react with the change in the potential of the source, for which we can replace the Vt with Vt0 plus gamma times square root of 2 phi f plus Vsb again minus 2 phi f. Now let us try to expand this value of Vsb again. So again Vsb could be written as Vs minus Vb, and that leads to Vout minus 0, since because the body of our NMOS is basically connected to the ground, and generally the Vout will be written as just Vsb. Now let us try to perform a partial differentiation on this current equation. Now one thing we have to note here, clearly the partial derivation is basically upon Vout, and inside this current equation we have the source terminal with respect to VGS, and also there is a source across the VDS term. So it means that this current equation has two functions with respect to Vout. One over this VGS, and again even across the VT there is a term that relates to Vout and through our source potential. So we basically have two functions over here, and as you guess, in your pre-primary schools you would have learned how to perform a partial derivation if one of the term is equated to u and the other term is equated to v. So I just try to recollect what was being taught before. That is, the partial derivative of u v could be written as v dot partial derivative of u plus u dot the partial derivative of v. So now let us try to replace the current equation with respect to these expressions that we have got here. So again, rewriting this current equation, and I'm just going to substitute the values of VGS and VDS and probably VT I will hold for a while. So replacing all those terms over here would lead us to a kind of expression something like this. And again 1 plus lambda is connected to VDD minus Vout over here. Now let us try to perform a partial derivative on this current equation with respect to Vn. Now what happens here? As I stated, this is our u term, and this would be our v term, and what we wanted is something to look like this. Now, let me go with this first equation, or the first derivation, by equating like this. Now, v term is nothing but 1 plus lambda vdd minus v out, and this would be my v term into the partial derivative of the u term. So, because there is a square term over here, it would be something like this: 2 into v in, v out, vt, and then the internal partial derivative. So what happens when we derive when we perform something like this? That is, partial derivative of v in with respect to v in is nothing but this would be equal to 1. So I am substituting the value of 1 in the place of v in. Now, how would we replace this particular term? So this could be written as v out with respect to v in, and next comes the vt term. Now, this vt is nothing but it's a partial derivative of vt with respect to v in, and we can also use a chain rule to rewrite or to represent the same expression. So using a chain rule, we can write something like this: partial derivative of vt with respect to v out multiplied with the partial derivative of v out with respect to v in. So why we have used this partial derivative is, in the previous expansion, we found that the value of vt is not a function of v in, but it is a function of v out. So performing a partial derivative with respect to v out would be a proper than compared to performing a partial derivative of vt with respect to v in. So that's the reason why we utilize a chain rule over here, and then we try to compute the gain expression. So having said that, let's move on to the next page, and let me try to redefine our VTH, and then later on we will try to expand this. So now performing the partial derivative of this with respect to v out could lead to, since because this is a constant, this would turn around to be 0, and then even this one, there is no term that is related to v out, so it is again a constant that turns out to be a 0 value. Now the leftover term would look something like this: 2 phi f plus v out, and again the partial derivative of v out with respect to the partial derivative of v out is nothing but is equal to 1. So we can replace this entire term as it is a multiple of just 1. Now what could be this term? I guess you might remember right now, this term is equivalent to a factor which is known as eta, which we have done when we discussed about common source amplifier with source degeneration. Okay. So this particular term is nothing but the value of eta, and we are going to incorporate the same back to this particular expansion. So what we have here is this whole bunch of term, and I forgot one more thing, the inclusion of this half k dash w by l. So anyhow, we'll be including that, but before that, let me try to write the value that we have got for the partial derivative of del vt with respect to del v out. So the partial derivative of that is nothing but the eta, and since we have already used some chain rule here, I have to add this particular multiple over here, which is again del v out with respect to del v in. Okay. And this entire term that we have got right from here to here is nothing but is the answer for this del u term, and the v term is here. And again, we have to add this particular term as a multiple for this entire term. So which is again half k dash w by L. Now here there are two terms that could be cancelled. And now comes the question here. So what is this k dash w by L and then the whole bunch of terms that we have here along with this 1 plus lambda vd v out? So I'm just going to make sure that you understand what exactly is these things. I'm just going to plug a part of this multiples into a single term, which is nothing but it's going to be equal to the value of gm. So gm, we know it is nothing but k dash w by L vgs minus vt, and this is where the vgs minus vt term. But you might wonder, what is this particular term? Now, whenever we try to evaluate the value of gm, we never consider the current to have the channel of modulation. But if at all, if the current has a channel modulation factor, then the original gm of the current that carries the channel modulation could be defined as gm equals to k dash w by L which is minus vt with 1 plus lambda vx. So this is the actual term for the current that has the channel modulation. So that's the reason why we could able to couple all of these terms under a single term as gm. Moving to the next page, the value of one expression is nothing but gm term that we have got when we perform the first term, that is u dot del v. Now we'll just move on to the second term, which is nothing but v dot del u term. So this I'm going to equate to the second, and later on we will plug both these expansions in order to get back to the gain expression. So looking back to the previous expression, what we have here is this whole bunch of terms, which I will just copy back to the next page. This is the ideal expression that we have, and as I said, we have to perform v dot del u. Now in this case, the v term is this, and I think I have done something wrong with the discussion. Basically, the first term that we have got here is basically v dot del u, and the second term that we want to calculate is basically u dot del v. Now, equating that over here, that is the second term, which is u dot del v, would lead us to something like this. So, I'm just going to represent this half k dash w by L into the entire u term, and we are going to perform the partial derivative with respect to the v term. So when we perform the partial derivative of this, clearly the first term is basically a constant which leads to a value of 0, and again the term vdd is again a constant which will again evaluate to 0. So the only term that would be left over is nothing but it's lambda into minus del v out with respect to del v in. And again, when we look back into this part of the expression, this expression is nothing but the current expression at the edge of saturation region. So I'm just going to equate this expression as ID and then multiply it with lambda and then again multiply it with minus del v out by del v in. So now let us try to combine all of these expansions. The term that we have written right now is nothing but it is equal to del id with respect to Vn. So we have to multiply this entire term with respect to the resistance R. And now moving all of V out with respect to Vn towards the right hand side could lead us to the following expansion. And over to the right side, the only term that we have is just Gm and RL. So now, what would be this product of del times ID? We know R0 is defined as 1 upon lambda ID, and due to this expression, we could replace the term id into lambda as 1 upon r naught here. Okay. And again, looking back to this equation eta times gm, we know the gmb is defined as eta times the of gm. So with this definition, we can even replace this particular term with gmb. So now that we have almost placed all the expansions into proper position, we can write the gain as del V out with respect to del V in, and that is equal to gm RL divided by 1 plus gm plus gmb plus 1 upon r naught into the total thing is being taken out with respect to RL. And this is the term that we end up for the gain expression. Now, let us try to cross multiply this particular term R out to the other end, and that would again simplify the expansion R naught, and we know that we can plug gm plus gmb as gm prime, which I write it as gm prime times RL into R naught plus RL. So this entire term that we have got at the bottom is nothing but is the equation that we find when we look from the drain. The resistance of RL could be nothing but this entire term, so which we normally take it as Rx. So if you could able to remember that this quantity is purely an Rx term. Now let us try to simplify this expression in order to gain some intuition behind this particular gain expression. So the very first assumption that we are going to assume is the lambda equal to 0, and the body effect also will consider it to be nil. Now when we adopt these two simplifications, what happens is the 1 upon r naught becomes 0 here, and due to which the gain will be returned as just gm RL divided by 1 plus, again there won't be any GMB term just because we have assumed that there is no body effect, and the only term that would be left over would be GM times RL. Now let us try to plot the value of GM with respect to V. Now clearly the value of GM would be of this, because we know that the gain expression when we wrote, we defined as V out with respect to V in is nothing but is a product of del ID with respect to del V in into the resistance RL. And what is this particular term? This particular term is nothing but a capital GM of our circuit, and this could be overlooked something like this. So what I have here is an RL, and I took off the RL out of this expansion, and what would be left over would be my capital GM of the circuit. Now let us try to plot GM with respect to Bn to gain some intuition behind this. And I'm just going to have a graph where x-axis is defined to be Bn and the GM is defined in B with respect to y-axis. Now till the Vn reaches the value of Vt, there won't be any current, and we know when there is no current, the value of Gm would be, I think, 0. Now, once we cross the value of Vt, the current starts increasing. Once the current starts increasing, even the Gm will also starts increasing. And because of that, the Gm starts increasing. Now, after a particular value of Gm, what happens is, probably this particular term would actually gain much more value than compared to the value of 1. Which means that this will have a higher value than compared to the value of 1, and this term could be approximated to be just something like this, and this approximation is valid only when the Vn has crossed some part of our VGS value. So under that condition, the value of Gm is so large such that the product of Gm into RL becomes much larger than the value of 1. Under that condition, the Gm could be approximated to be equal to 1 upon RL. So this is an approximate value. So what is the conclusion that we can derive from here is that once we cross a particular value of Vn, the GM of our circuit becomes almost constant. And that is the one that we have already seen. This kind of graph we have already seen when we discussed about common source amplifier with source degeneration resistance. Now let us try to plot the gain. So again, the gain could be written as the product of capital GM times RL. I'm just going to use a different color to plot the gain expression. And clearly, when the value of Vd is less than 0, the value of Gm is basically 0, and because of that, there won't be any gain after this. Once the value of Vn crosses the value of Vd, then what happens is the gain starts increasing. And once the value of Gm reaches a particular value, then what happens is the capital Gm could be returned or could be approximated with just RL as we have shown earlier. Now, due to which the gain after a particular value of Vn, it becomes equal to 1. That is, the maximum gain that we can get out of this common drain amplifier could be 1. And the maximum value of capital GM that we can get out of this common drain amplifier is just 1 upon RL. Okay. So that is the intuition that we can derive from here. But the gain that we have calculated right now is based on the approximations that we have used. We have actually neglected one of the important side effect of it. That is, we have neglected the impact of body effect. If the body effect is taken into account, then the gain could be returned as 1 upon 1 plus eta term. So I will leave this computation of this value to you. You can just verify. Till now, we have developed the intuition behind this gain of our common drain amplifier. Now let us go for a crooked method of finding the quickest gain using a crooked method. It's not actually crooked, but I use it. So I think we already know from the network theory what is meant by voltage division rule. So we are going to use this voltage division rule in order to compute the gain expression. So let us try to bring back the common drain amplifier with the resistive load RL. Now, looking from this source terminal, that is looking from the Vout node, what we see down is basically the resistance RL, and this RL is going to be in parallel with whatever the impedance that we are finding through the source terminal. And we have already computed that the impedance when we look through the source terminal is nothing but it is equal to 1 upon Gm in parallel with 1 upon GMB in parallel with R0. We have already discussed about how all the three parallel resistors fall apart across the gate, drain and body with respect to the source terminal. So now we are going to use it for the quick computation of the gain for the circuit. So now let us represent the transistor M1 in terms of these resistances. Now when we look up, we have three parallel resistors, and those three parallel resistors has to be connected like this. So this 1 upon Gm is basically connected between the gate and the source, and the value of R0 is basically connected between the drain and the source, and the 1 upon GMB is basically connected between the source and the body terminal. Basically, the drain is connected to the ground, the AC ground, even the body is basically connected to the AC ground. Whereas the gate is basically connected to the value of Vn. We are going to use a simple analysis here. As we know, that the resistance R0, the resistance 1 upon GMB, and the resistance RL are all having the same node. At this point, there is the source node, and the other end of those resistances are all connected to the ground. So if I have such kind of condition, we can put all of these three resistances into a single resistance as a parallel combination of all. So redrawing the same circuit, having 1 upon Gm being connected between the gate and the source, and having all the three resistances in parallel that is connected between the source and the ground. So the resistance that we have here is nothing but R0 parallel with 1 upon GMB in parallel with RL. Now here is my Vout. Now our intention is to find the Vout with respect to Vin. So because of that, we will try to identify the Vout. Now Vout is basically the potential drop across this particular resistance, whereas Vin is nothing but it's a potential drop across both these resistances. And we know that if we want to know what is the value of Vout, it would be this resistance divided by the summation of these two resistances multiplied with the total potential. So having said that, let me try to represent them as a voltage division rule. So this is my resistance that is seen across the node Vout divided by the summation of the resistances, so which is 1 by Gm plus the three resistances that are in parallel, and that has to be multiplied with the total potential Vn. And now the gain is nothing but Vout with respect to Vn, and there is all this whole expansion. Now that you can just try to manipulate this equation and then try to get back this expression. So I will leave this particular result to you so that you can utilize this expansion, like try to uncover the parallel combinations and then put them in proper notations and see whether this particular gain expression is the same as we have got during our large signal analysis. Please verify. Now let me take one more example, which is nothing but the common drain amplifier with a current source load. Now, or the load transistor M2 could be modeled with the equivalent resistance of value R01, and again by using the same voltage division rule, we can quickly identify what is the relation between this Vout and Vin. So in the place of R, what we have is just R01, and we will end up with same kind of expression even for the circuit that we have it here. That completes the discussion of common drain amplifier. Thank you.